Welcome to the Fundamental Theorem of Calculus, part 1 of this topic. So the Fundamental Theorem of Calculus. Suppose f is continuous on a closed interval from a to b, then g of x is equal to the integral from a to x of f of t dt, and then g prime of x is equal to f of x, and using the Leibniz notation, this would be the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. And the second part is that the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative of lowercase f. That is a function capital F such that capital F prime is equal to lowercase f. And we could see that this would just give us the area underneath the curve y is equal to f of t. And it stops at whatever value x this is referencing. So as an example, using this graph, if f is a function whose graph is given by g of x is equal to the integral from 0 to x of f of t dt, we want the values of g of 0, g of 1, g of 2, g of 3, g of 4, g of 5, and then sketch a rough graph of g. So g of 0 at this particular beginning point on the graph. This would just be the integral from 0 to 0 of f of t dt. And one of the properties of integration is that's just 0. So 0. G of 1. This is the integral from 0 to 1 of f of t dt. But from our picture here, that would be this triangle here. So this is the same thing as 1/2 times, we have 1 here as the base, times the height, which goes up to 2. And that gives us a value of 1. G of 2 is the integral from 0 to 2 of f of t dt. This is the same thing as the integral from 0 to 1 of f of t dt, plus the integral from 1 to 2 of f of t dt, since we now add in this rectangle here. So from g of 1, that just gave us 1, plus from this rectangle, then we have a base of 1 times the height of 2, so 1 times 2. This would be 1 plus 2, so this gives 3. For g of 3, this would give us the integral from 0 to 3 of f of t dt. This is the integral from 0 to 2 of f of t dt, plus the integral from 2 to 3 of f of t dt. And this is 3 plus, for this integral from 2 to 3, that's this area here, which has this curved portion, which we could estimate to be about 1.3. So this area here is roughly 4.3. And we add 3 in the 1.3. For g of 4, this is the integral from 0 to 4 of f of t dt. This is the integral from 0 to 3 of f of t dt, plus the integral from 3 to 4 of f of t dt. And so, as I just fixed my t on here very quickly, that adds the area underneath the curve down over here. So we got 4.3 from the previous part. Since this is the area underneath it, we're going to subtract this value. And we're going to subtract about 1.3 again. So this would give us a value of 3.0. And to get g of 5, I'll just write that one up here. G of 5, this would be equal to the integral from 0 to 5 of f of t dt. So integral from 0 to 4 of f of t dt plus the integral from 4 to 5 of f of t, not x, f of t dt. So this would be 3.0, again, minus because of this part below the curve. Again, that would be about 1.3. And this would give us an area of 1.7 in total for up to that point. And a rough sketch of what this would look like. Let me quickly do that. So go up to 5 on the x-axis, up to 4 on the y. This would have a maximum of 3 due to the point that, well, what we found that g of 3 is the highest, and that being above 4, so we would slope up to that, and then this curves downwards and stops at around 1.7 there with 5. So a graph looking like something like that. For example number 2, we want to find the derivative of the function g of x is equal to the integral from 0 to x of the square root of 1 plus t squared dt. And this gives us very nicely as the answer of the square root of 1 plus x squared as our answer for this. For the third example, the integral from -2 to 1 of x cubed dx. So for this, we would get 1/4 times x to the 4th. And we want to calculate that between -2 and 1. So this would be 1/4 times 1 to the 4th minus 1/4 times -2 to the 4th. So 1/4 minus 16/4. So 1/4 minus 4. This would be -15/4, or as a decimal, -3.75. Let me know if you have any questions or concerns, and be on the lookout for part 2. Thank you.